Welcome to the AI for You Cafe for live presentations around AI. As always, we are waiting a little bit until all the participants are coming in. Thank you for joining us today. In the sunny weather here in Cologne, it's very sunny. With us today is Mihai Daktu from DLR. Thank you for being with us. Hi, Mihai.
Hello, good afternoon.
I will introduce you very soon. The theme today is CANDELA Earth Observation Data Mining Tools, a tutorial. And my name is Carmen McWilliams, and I'm the moderator and organizer of this cafe session. And I'm the director of the company Grassroots Arts, which is a partner in the AI for You project funded by the European Commission. Please take notice that the session will be recorded. The link for the recording you will find later on the AI for You YouTube channel if Mihai allows it afterwards and gives the permission to publish it. No confidential information shall be shared in this cafe. All speakers express their personal views and opinions. This is not necessarily the official AI for You project opinion. Again, for somebody who has been here for the first time, what is this cafe about? This cafe is an online forum to gain insight into the European AI scene, and participants get to share a chance to share knowledge and experiences and meet stakeholders from various areas of AI research and applications. So I was asked often by you, can I share this invitation when I get one by email? Yes, this is a public live cafe. Please share it in a network to friends or colleagues who are interested in AI topics. It's important AI topics. We are talking not about something else here. And it's interactive. So you may ask questions to Mihai. He will make his live presentation for about 30 minutes. And then afterwards, he will take your questions. I will read them to Mihai. So please type them in the chat. There's a chat on the right side. The control panel called question chat. If you also wish, you can also raise your hand, and then you have the audio function, which there you can even ask the questions directly. So now we come to the main point, to me. I will introduce him shortly. Mihai Daktu received his master and PhD degrees in electronics and telecommunications from University Polytechnic Bucharest in Romania in 78 and 86. And 99 he received the title of Habilitation à diriger des recherches in computer science from University Louis Pasteur in Strasbourg, France. And currently, he is Senior Scientist and Data Intelligence and Knowledge Discovery Research Group Leader with the Remote Sensing Technology Institute, IMF, of the German Aerospace Center, DLR, in Oberpfaffenhofen, and Professor with the Department of Applied Electronics and Information Engineering, Faculty of Electronics, Telecommunication and Information Technology, UPB. His interests are in data science, machine learning, and artificial intelligence, and computational imaging for space applications. He is involved in big data from European space, ESA, NASA, and national research programs and projects. He is member of the ESA Big Data from Space Working Group. So there's many more things to say. But I'm now handing over to Mihai himself. I will make you the moderator, Mihai. So I change it, and then you can speak for yourself. And again, thank you that you're here, and welcome.
Thank you very much. Thank you for inviting me. Good day, everyone, and thank you for attending this presentation. And I will go straight to the slides. Try to organize my screen.
Yeah, I see them. CANDELA. Yes, perfect.
Today's topic is Earth observation data mining, presentation of tools, tutorial-like presentation. I organize a material introducing the CANDELA, an Horizon 2020 project. an introduction about machine learning and data mining, and continuing with details on architecture and the function and operation advantages of data mining as a component of artificial intelligence in Earth observation, concluding with a demo of the tool. About the CANDELA. So CANDELA, it is an Horizon 2020 project. Copernicus Access Platform Intermediate Layers Small Scale Demonstrator. Copernicus program, it's operating highly technological advanced Earth observation sensors in space, multispectral synthetic aperture radar, atmospheric. The novelty and the great impact of Copernicus, in addition to the high technology of the sensors, it is the open and free access of the data. The technology provides acquisition rates of hundreds of terabytes per day. This resulted in a huge volume of data, also an important diversity of the data because of diversity of the sensors. With a high rate, multi-temporal coverage of global Earth. This results in big data, and big data means collecting data, but big data means also technologies to exploit the data. The objectives of the CANDELA project, it is to develop a system which its operating algorithms and paradigms for accessing, putting accent on artificial intelligence like discovery and processing information, and delivering this information and knowledge to users of Earth observation data. The kernel, the core, it is information retrieval, data mining based on machine learning techniques. Definitely, that relies also on interoperability in such a way to take advantage of all the assets which exist in Earth observation and to have an impact valorizing, increasing the economic impact of Earth observation application. Another important concept in the CANDELA Horizon 2020 project, it is reuse and openness. So the platform aims to become as open as possible. At least the data mining tools today, they will be fully open for access. These tools, they have evolution, and evolution in the sense of scientific content of the algorithms which are integrated, but evolution in the sense of technology readiness level. So today being operational. This high technology readiness level, it is an asset of extremely intensive engineering work, but also of collecting detailed requirement from the Earth observation user community. And that is very important in artificial intelligence because it is allowed to drive artificial intelligence to practical problems. Inside machine learning. Machine learning is covering, among other topics, supervised learning. In the supervised learning, in a simplified way, we have to deal with two steps. In the first step, the training, we have to use labeled data, pre-labeled data. In the example, in the bottom, there are, let's say, several classes like water, volcanoes, forest. This data is very important. So somehow in artificial intelligence, the training data, it is as important as the algorithm itself. So generating meaningful training data, carefully designed, is very important because the machine learning is learning to generate the data model, the model which will be used for classification from this data. So in the first step, the training data set is presented to the machine, and the machine is learning, is generating a model of this data. In the second step, the classification, the unknown data, it is presented to the machine, and the machine is using the previously learned model to label, to assign unknown data to the classes which have been defined. So we have a process of learning and later applying the body of knowledge. Let's say the model is a body of knowledge which was created and apply to a very large data set and sort this data according to this extracted knowledge. In artificial intelligence, among other kind of machine learning, we have active learning. So active learning is a very particular procedure in which the machine is interactively interrogating a user. The user is an information source. It interrogates the user to label new data points with a desired output. So active learning is a dialogue. So it's different from the previous, let's say, usual two steps, machine learning, training and classifying. It's a dialogue. The user is examining the data. For instance, in the bottom, he's selecting, giving green, a positive example, volcanoes, and he indicates he's not interested in water or forest or other classes. So he's separating the data in data of interest and data out of the interest of the user, so positive and negative examples, the dialogue. The machine understands his intention and creates incrementally a model and presents to the user the result of sorted data. This dialogue allows to select the data in a better way. To understand the advantages of active learning, I make a short comparison using 5 criteria: the training data volume, the trained data volume, number of classification accuracy, and training speed. And comparing the shallows, let's call it classical machine learning, deep learning, which is very popular and is dominating the research area in artificial intelligence in the last 2 years, and the active learning, which is implemented in a CANDELA data mining tool. So regarding the training data volume, the training data is a data which was previously labeled. In classical machine learning, this volume of training data already labeled, known reference data if you want, it's order of gigabytes. In deep learning, the volume it's growing, it's really big data, this could go to petabytes level. In active learning, the training data, the known data, the reference data, which should be presented for generation of a model is very small. It's under kilobytes. It's very, very small, few samples of data. That is a huge advantage, mainly in remote sensing, because in remote sensing, we do not have labeled data. Also, labeled data is very specific for every application and for every sensor, and have many, many sensors and many, many applications. And that means having a small training data set, which is needed. This means the training data set can be verified carefully, because the training data is very important. Training data is as important as the algorithm, the classification algorithm itself. So active learning, compared to this shallow machine learning and deep learning, is using an extremely small training data. Advantage in Earth observation, because this training data can be verified. This means it's increasing the degree of trust in the model which was generating in the classification. The second criteria for comparison is a trained data volume, the volume of unknown data which we want to explore, we want to classify, to extract information. For the classical machine learning, the volume of unknown data is generally gigabytes to terabytes. Deep learning definitely it's going in the direction of big data, petabytes. Active learning maybe is not competing deep learning, it remains at level of terabytes, gigabytes, terabytes. But compared to the ratio in between the training and the unknown data which will be classified, this ratio is huge. So this ratio is beating the deep learning. So active learning, in terms of the power to generate new level data, it's much more efficient compared to deep learning, and definitely with a shallow classical machine learning. In terms of number of classes, in shallow machine learning, number of classes is tens, maximum 100. Deep learning is the same, could be around 100 classes which could be extracted from our unknown data. In active learning, the number of classes, it is not defined, it's open, it's defined by the user. And that is again, it's an important advantage in Earth observation. If we are using a pre-trained data set in which we have, let's say, 10 classes, 2 classes of agriculture crops, 3 classes of forest cover, land cover, urban areas, for instance. In the application, the model is learning only these categories, and the unknown data is explored only for these categories. So both shallow and deep learning, they are limited in the number of classes, and another limitation is that these classes are fixed. The unknown data is explored only for this predefined trained data. In active learning, the classes are defined by the user. They are opened. And actually, remote sensing and artificial intelligence, they have a common objective. So remote sensing is to investigate remote areas where you do not have information by other means. These are unknown areas. You could have unexpected classes, and you need to discover this. Artificial intelligence has the same objective. In general, for all areas, not only for observation, artificial intelligence should reveal hidden information in large volume of data, reveal and explain it. And active learning is a tool which is open for this. It's adapting to the user, allows the user to discover classes and to label classes. In general, as a figure in very high resolution data, as TerraSAR-X data per radar at 1 meter, the German mission, we have about 1,000 classes for urban areas. In Sentinel-2, we go to up to 100 classes up to now, but this classes is opened, and these classes, again, they depend, adapted to their, depending on the conjecture of the user. Another criteria for comparison of this method is classification accuracy. Classical shallow machine learning, in average, 85 could be better. It's taken from the state-of-the-art applications. Deep learning is getting better, in average 90%. Active learning, in average 85%, remains, let's say, not so competitive as deep learning, but because of the flexibility, agility of the method, it's extremely useful. The training speed, which is our last criteria in this comparison. For shallow machine learning, it's hours, or less than 1 hour. Deep learning depends on resources, but even on large, on high-performance computing facilities, that could last days for training and generating the model. Active learning is very fast. It's seconds to minutes. It is real time to the speed of reaction of the user. So it's a dialogue, clicking with the mouse on the image, getting the response, responding again, clicking again on the screen on the image, indicating positive, negative example, and the answer is coming. So it's very fast. And this speed is very important because that allows to explore large volume of the data in a very flexible way, discover new information and knowledge. What is data mining? Data mining is a process of discovering patterns in big data and is based by a synergy fusion of methods in machine learning, statistics, and database techniques. Machine learning, because we have to learn models, relations. So data mining means discovering mainly relation among the entities in the data. Statistic, because we need to analyze the models are statistical, the analytical of the data is a statistical measure, and we need database techniques in order to be able to very fast manage, structure huge amount of data. In CANDELA projects, the data mining for Earth observation implements 2 main functions. The first is image search and semantic annotation, which aim to discover and semantically label the Earth observation image. This is an image information mining. It's an active learning. It's an image information mining because it refers to the basic content in the image. The content in the spectral signatures or in the radar signature of the sensor. It is semantic, and that is very important because it's recording in the database not only a label, an abstract label, but it's indicating the semantic used by the user. And this allows to share information and knowledge. Semantic is very important in communicating the results inside of communities. The second function of data mining in Earth observation is a multi-knowledge query. It aims at a knowledge extraction from the EO product, including metadata and image like location, time of acquisition, sensor, imaging modes, and all the metadata of the sensor, so product, and also including the image semantic labels which are generated by the user. They are depending on the application, or the image descriptors extracted for this purpose. So that is a multimodal query because it's operating not only on the image, but also on semantic and on textual and numerical descriptors. And this is based on database technologies as SQL. So what is in the data mining tool in CANDELA? So we have in principle a module for annotation interface, a database management system, a multi-knowledge query, an image search and semantic annotation, which are implementing the data mining functions. These are interactive modules supported by human communication machines. And in addition, important for artificial intelligence, we have a system validation module in the sense that the results which are produced by data mining, they are not only classes or semantic labels, they are accompanied by a measure of trust, a certitude. We start with the Earth observation product, which could be a synthetic aperture radar or a multispectral Sentinel-1 or Sentinel-2 product, for instance. This product, it is processed and it is cutted, is generated partitioning tiles. So tiles are typically in between, let's say, maximum 300 by 300 pixels to 30, 25 by 25 pixels, a multi-grid tiling. Each of the tile is processed to extract signal, descriptor, spectral signatures, or synthetic aperture radar signatures, or image parameters like texture or geometrical descriptors. And all this information, it is stored and managed by the database. So the semantic catalog, it's recording the semantic generated by the users of the system, which they are typical classes. Users, they can find, they can discover in the satellite images like park, agriculture, sea, airport. Metadata, which is very important, all the metadata from the product, from the Earth observation product, it is recorded in the database because it's important to understand all the data, including geographic location, time, and sensor information. The human-machine communication, which enable to operate the system, they present the product and the tiles, and also the result of the classification, which is marked in blue. These modules, algorithms, and database technology, it is integrated in the CANDELA platform developed by others. The CANDELA platform accesses GIAs, Creo GIAs, using Sentinel-1 and Sentinel-2 products. There are two containers, one which is a data model generation, which is tiling the products, extracting the metadata and the basic attributes, the features and descriptors of the image. And another container with a data mining database, which is a MonADB database, which is containing the validation database to operate with active learning. These are accompanied by a number of interfaces, like Jupyter Lab, which are connecting to an interactive part. the knowledge discovery interface, the human-machine communication, which is operated by the user and communicates with the platform. So we disconnect in this operation data mining from the classical use of a platform and Dockers or Jupyter notebooks, which are processing on a batch and they are operating with the scripts. We go to high-level operation via human-machine communication and intelligent way to access data, and also very simple. Data mining in action. The first step in operating with data mining, it is searching in DIAS, in CREO-DIAS in a particular case of CANDELA, searching the products and loading the data. So this is an example of searching Sentinel-2 data from the area of Munich with a cloud cover and giving some information, for instance, the time window for the acquisition. The query in DIAS result in 24 products which will extracted as they are listed. The user is selecting the product and is starting the data model generation, in which has to indicate the size of the tiles, 120 pixels by 120 pixels. For resolution of 10 meters, that means 1.2 by 1.2 kilometer area on the ground. Number of grid levels. The tiles are actually cut in this case in squares of 120 by 120 pixels, 1.2 by 1 kilometer, and later they are again split it in a finer grid of 60 by 60 pixels, and in another finer grid of 30 by 30 pixels, in such a way that it's possible to obtain a classification of mapping of the class in a finer spatial grid, but also to obtain diversity in the semantic. A simple example, on an area on ground of 1.2 by 1.2 kilometers, we have several objects. We can have a group of houses, a highway, a lake. And if we make the semantic annotation as a level of a patch of 120 by 120 pixels, we will call this residential area. So semantically, it's a residential area. When we make the partition in smaller patches of 60 by 60, we obtain 4 patches. One contains a lake, one contains the houses, one the highway. And the semantic attached to these patches is different. It's lake, highway, road, and houses. So the partitions, the multi-grid approach, has 2 advantages, 2 objectives: to have better localization in space and diversification of the semantic levels. We indicate the type of the product for the ingestion. We indicate the type of features to be extracted. This is very important. We operate with features like texture descriptor, like Gabor or Weber descriptors, or with multispectral histograms. The texture descriptors they refer to spatial information, and they are very strong for the urban area or forest. Spectral features they are very important in applications which are going to physical models like water quality, agriculture, because in the spectral indices we obtain physical information about the scene. It's possible at the data ingestion to select the bands. In this example, have been only the 10-meter bands of Sentinel-2 selected, but the system can make any combination of using all the 13 bands of the sensor or any other sensor combination adapting to the type of sensor. When the data generation was running, the result it is stored in the database, in the tables. So each of the feature has a table for semantic features, metadata, and the information in the database is now operated by a human computer interface, which behind has the artificial intelligence, the active learning. the graphical user operation is based on a number of simple functions. So a query as a database, a training, which it's activating a support vector machine in synergy with a Bayesian decision. The changes a grid level, so we can working on 120 or 60 by 60 or 30 by 30 pixels. So this grid level can be defined as a data ingestion. Loading fetches, it's a visual browsing of the result of the query. If you want, it's a reusable function. Operation to ingest in the database the result as a classification as a semantic level, which later can be used in queries by SQL. Operating going in between images, because we operate with many images in a spec on the interface, image ID, reset on this layer, reset all the training, show the training samples, it's a reminder, export annotation, and definitely the function to benchmark the measure. So in the system, there are already ingested labeled dataset, or the user can create its own labeled dataset in such a way to allow the benchmark and to generate quality measure for the classification, which usually called or other classification indices. How the interface it is operated? The interface is operated with the left and the right mouse buttons. The left indicates positive example, the target of our classification, water bodies, this example, and the negative, the mouse click on this image, the different classes which are distinct from the target of the classification. So in this example, we want to obtain classification or labeling of water bodies. We give a positive example and a negative example, and the system is grouping together all water bodies, and it's separating from other kind of structures. The system is grouping this in, let's say, an intelligent way, in the sense these are the most relevant patches relative to the target, to the model which is trained, and these are the most ambiguous. This presentation and grouping, the choosing of the machine learning in most relevant and most ambiguous is very important. The user is looking in among the most relevant, is browsing them, and can find easily examples which are negative examples. It's easy to filter out to correct the model. And the most ambiguous, they allow to detect the positive examples which are wrongly classified. So browsing on this, selecting on this sorted data, the user is easily correcting the training. During the training, it's using 3 to 10 samples per interaction. And the number of interactions, it's 3 to 5 interactions. Definitely, the result of the classification depends on the selection. However, because this number of samples is very small, the user can control them, can decide about the training data set in the active learning paradigm. In the second iteration, the user gives another positive, another negative examples, and at the end, when he's satisfied with the quality of the grouping of the labeling, he's inserting the label in the database, and the database will create a link to all the patches in all the products which contain this label in the dataset which was operated in the session of labeling. Further, these labels can be accessed by SQL, and they can be object of multimodal queries and knowledge discovery. In the benchmark function, for the classes which are in the reference data set, like main intensity or C, the system is automatically computing accuracy of measured precision recall, and also is presenting the course for precision recall and the log. It's the same for each of the class. So that is important to have always a verification of the benchmark. It's a very important operation in artificial intelligence. Demonstration. So we have a Sentinel-2 image. We indicate with a mouse with clicking left positive and right negative mouse. Example, the target was the forest, which is the area covering this part of the image. Negative example has been given to separate from the cloud and other kind of vegetation in the fields. In this window, I have the most relevant, which shows that actually the system already understood quite well the class and separates from other kind of vegetation like land cover here. However, in the first iteration, there are still false alarms, like false negative. That's why it's positive to examine the image to evaluate which is the amount of data which is incorrectly labeled, and examine the most relevant and the most ambiguous. So
it's me, Carmen. Hi, I'm just disturbing you. I think you may the quality of your audio is really going out. And so maybe the video, the trick is maybe you switch the video yourself.
Thank you. Thank you. I come close. I tell you what happened. My computer got overheated and the fans started.
Okay.
So this is a noise, 30 seconds.
Okay.
Now, in the process, the user continues to give a negative example. In between, he goes to the next grid from 120 to 60 by 60. So has a final grid. And at this point, is satisfied, let's say, with precision of the classification. He's labeling the data, sends the labels to the database, and the labels of 120 pixels by 120 pixels and 60 by 60 pixels are now indexed in the database, and they can be further analyzed quantitatively or semantically together with all the other related database information. So I would conclude in here with a demonstration and the presentation, acknowledging the support of my colleagues, Dr. Vegao and Dr. Cornelius Dimitri at DLR in the Data Intelligence and Knowledge Discovery team. Thank you for your attention, and definitely I'm open to answer questions, trying to cover the thermal noise of the computer.
Okay, thank you. Sorry for interrupting you, but there was like there is a little issue with the audio sometimes when many people are at the same time using the internet. It's always the same. So thank you very much for this very engaging talk, and I hope you as participants also have questions. Please write them in, because Mia is now there. You can ask it now. Write it please in the text box. I start as always. I have a question again, which I keep asking. I'm talking for all the SMEs and PhD students and researchers out there. How can I access this platform? Can I use it as an external person, or is it available? How?
Yes, so in this moment we have a version of the platform. No, the platform, it is in the framework of the project and it's operated by Athos. Athos is open to discuss the use of the platform. In terms of the data mining tool, which is developed by DLR, we give the tool open source. So if it's in this moment, if someone is asking us, sending an email, we respond and we will share the tool. At the end of the project, at the end of this year, the tools will be on the CANDELA platform. We also discuss maybe to make this public on other platforms in the framework of Horizon 2020 projects. So the answer is yes, it's open source. In this moment, by request by anybody, and by the end of the project, that will be available.
Okay, so it means like practically, I would now write you an email if I would be somebody interested, and that would be processed by Atos and you, no? But I would write you an email. So if somebody in the audience wants to use it, the best way to write me or an email, and I forward it to you. That's the way, right?
Yes.
Okay, so just to know. The second question was, will the presentation be available?
Yes. Yes, sure.
Good, because I did.
Yes.
Wait, because there was the question of moving out, and now comes more questions from the audience, from participants in. Hi, how can we engage to use this system? Are you planning to evaluate it? This is the question from Katerina Salamova. The question is, how can we engage to use the system? Are you planning to evaluate it? And let's see, maybe there was even a third one. In which direction?
Yes, so we already did several evaluations.
Evaluate. Yes. Okay. You go.
Yes. Okay. We already did evaluation. Evaluation, it's a growing spiral process, because evaluation, it's a big data evaluation. So we evaluate the system in terms of scalability with a lot of data, and we evaluate the system in terms of scalability with variability of the data in different kind of sensors. We already, if someone is interested, also can address me, and I can present, I can send results which have been published until now in the validation. We had several steps of validation already fulfilled. We are now in the phase, in the CANDELA project, in the Horizon 2020 project, in the phase of finalizing the tool and proceeding with validation of the tool, both in terms of machine learning, artificial intelligence, and also validation of the users. The results will be published in the technical notes, documents of the project by the end of the project, and also in a publication which are under preparation now. Again, for details, I'm very glad to be in contact with the person which are. The validation goes, again, I want to stress, in terms of machine learning, precision recall, and also in terms of satisfaction with the users, which are different criteria.
Okay, thanks. Katarina says thanks for this.
Thanks, Katarina.
And here comes Marcelo Reinaldo de Sousa. Hello, Marcelo. Great to hear. Carmen, this platform Copernicus, which I've been taking a look at, is worldwide used? Question mark. Is this Copernicus worldwide used?
Yes.
That's a
so,
question.
Yes. Copernicus data, it's free and open for everyone around the world. The data is accessible on the European Space Agency hub. So searching on ESA Copernicus hub, and it's free access to any kind of data all around the world. And if you look in publications, also, which are very much visible, there are publications coming from China to Alaska, from Australia to Hawaii. People are using the data. And this is completely free, completely open. For any kind of application, there's no restriction.
Great. And now, Jose Maria Lazaro. Any plans to further develop CANDELA after the end of H2020 project?
Yes, we always do this because investment in space technologies is very high. And we try always to continue the development. And generally, at the end of a project, we have two branches. One branch, the tool which was developed in the project, as is the case now, will become open source. And we are glad to work in other projects or in application with people, or either to promote, to help people without being us involved directly, but to help people, open source if you want, to help people to develop the project, other applications. On our side, we are interested sometimes to have feedback because we learn from applications. And the second branch, at the end of a project, including this CANDELA, we learned from the users, and we continue to renew, to update the basic artificial intelligence, machine learning, statistical information theory algorithms, which are in the tool, even the tool itself, and to go to the next generation of tool. This tool is already in a series of evolution of data mining tools in the last 10 years. So we had already the third version. So every, say, 3-4 years, we issue a new version of the tool.
Okay, thank you. Now, I have a question. Like just more because I'm interested in these difficult times. I'm asking the same question. As I was in the Global Forum of AI for Humanity in Paris last year, there was like the G7 group, and there was the idea to use AI for solving the societal and sustainable development goals of 2030. And there was the idea also to fight with AI climate change and fight health problems like, for example, Corona in the moment. That's why I'm coming to this, and prevent hunger. Do you see like AI, I'm just asking this directly, do you see AI could help to solve environmental problems because you do Earth observation? Do you think that?
Yes, yes, I'm not thinking this. We are doing this, not myself, but also myself and my group, my colleagues, the DLR, ESA, and other teams. We are a community. Why? Because the climate, it's actually a big data. A big data not only in the sense of Copernicus, it's beyond Copernicus, because there are much more data types, much more sensors which are used in understanding the environment. The last years, it happened that climate is changing dramatically, and that's happened, unfortunately, or fortunately, I don't know, it's better I don't comment, with a moment when technology allows to process this data. So in the past 5-10 years ago, processing such a huge volume of diverse type of data was not possible. Today we can do this, and everything is now concentrated on doing this. Regarding the present situation with the coronavirus, the pandemic, there are already teams which they studied climate, atmospheric condition in relation to the intensity of the pandemic in various countries. And there are results which are already published. So if one is interested, there is a paper published a few days ago in archive. Okay, I don't have the title now. I have it on my computer, but it is, if someone can ask me, search in archive, you'll find it.
Yes.
And also in a term of Earth observation, and somehow independently of the pandemic, since a few years, the exposome extended Earth observations of the climate change environment has an impact on human life behavior. And the exposome now it's not only a topic of medical science or medicine, biology. Exposome now it's related to environment, and environment is observed by Earth observation. So Earth observation, artificial intelligence are tools to support monitoring health. Yes,
thank you. I'm totally with you, and I see that a lot of people are now coming. Natalie says thanks for this question. Gerard Kennedy, can CANDELA be used in real-time applications where time delay is critical?
Good. I try to answer. If my answer is not satisfactory, today's access to the Sentinel data from the acquisition, from the overpass of the satellite to obtaining the data, it's a day. Could happen that in next years with laser communication systems, the access to the data to the user will be much faster, hours. With this active learning, the advantage it is that you can, as soon as you have the data, you process, you have to transform the data in the database format and extracting the feature. This depends on the computation capacity everyone has. On a normal computer for the Sentinel scene, it takes half an hour. If you have a computer with 20 CPUs, which is a normal computer today at the end, that could be much faster. So with let's say with a cheap high performance computing, it's possible to be in a processing chain which goes closer to real time. So real time for the satellite bus today, 1 or 2 days until the product is published on the ESA hub. In probably 1 or 2 years, this time will be much faster. And that is changing the type of applications. So the time series, the time analysis is becoming a important scientific and business part.
Mm-hmm. Yes. So I think, thank you also from Gerard. Thank you for your answer. And now I think we're closing in, but Marcelo comes back. He asked before about Copernicus, and he has one more question. So one of the purposes of big data analysis in Copernicus project is predictive? Question mark?
In the CANDELA project, particularly in the CANDELA project, prediction is not one of the strong parts. It is possible to use a prediction because in the CANDELA, I don't know about the entire project, not only as a data mining tool. In the CANDELA, there are components, functions, services for change detection and multi-temporal analysis, and also for merging AO information with non-AO observation. So operating the CANDELA platform is possible to make to derive models which could support the prediction. In terms of observation, in particular for time series analysis, prediction is becoming a very important topic, and it is one of the challenges in artificial intelligence. It's a difficult task, algorithmic, to have a good prediction.
Yes, thank you. I think we are closing in the questions. If you, I mean, not you, Mihai, but you watching us, if you have more questions, please forward it to me. I can forward it to Mihai or directly to Mihai. Also, the recording, as I say, will be sent first to Mihai. If he says it's okay, I publish it on YouTube. It will be in the AI for You channel. And if Mihai allows, he sends me his presentation, and please send me the request because we are really interested who would like to have it. So please send it to us because the whole cafe is about matching and meeting people, and somehow maybe have more interest. Go in more details after this live session and to connect, no? To connect the people who have the same ideas about AI and are interested in the same theme. So now I again thank you, and I announce shortly the next session where I of course would love that you come. The next session will be next Wednesday because we are always trying to make it next Wednesday. One moment, I want to see if I can still see the next. Yes, I have it. Sorry, meant. Good. It comes. Meant. Next one. Yes. The next live cafe session will this time be somehow different because we have an historian and Irish storyteller who will tell us about the origin of computing, about the father of computing, which is George Boole, if I pronounce it right, and one of the first who discovered that maths can be used maybe to make intelligent machines in the future. We met him personally, our Cronan O'Doblin, and he's a great storyteller. He will lead us to original documents and letters from George Boole. So this is more something for everybody. So if you feel like inviting friends, it is public, and it shows also the variety of this cafe. And have a nice day. Enjoy the sunshine and keep safe, because we are still in the middle of a horrible health crisis, as we all know. And I thank you for you all joining us. Thank you, Mia, again. You are the second here. Yeah.
I thank you very much. I thank you, Carmen, for organizing this. You are doing this really fantastic. It's a fantastic job. I thank you for all attendees, and definitely I'm glad to receive as much questions. And take care and keep healthy.
Yes, thank you. See you soon. Bye-bye.
Bye-bye. Bye-bye.